Okay, so it's Thursday and we're going to finish muscles. I looked at how much we had left and I had forgotten how much we hadn't done yet. So this may take the rest of the lecture today, and that's fine with me. We have 8 hours of lecture a week. So I can do the nervous system next week in 8 hours. Yeah, okay. So I still have some of these discs up here if you want one. They're good for muscle. They're great for nerve. Absolutely good. Just perfect. And then they have all the systems you need for AMP2 as well. So if you can get it to play on your computer, it's definitely worthwhile. All right, so this was the last thing we did last time, so I like to start with that because y'all get a little brain dead towards the end of our 2-hour stint in the classroom. And muscle metabolism is important in ways that you might not really think about. So when you think about the metabolism of muscle versus other body organs, brain, heart, lung, liver, kidneys, skin, muscle metabolism outweighs almost all of those. I would say the only organs that pretty much routinely, whether you're awake or asleep or just working away, and have high metabolic needs are your brain and your heart. And of course, your heart does speed up with activity, right? Does your brain? Does it need more blood when it's active than it does when you're resting? Like if you're sleeping, do you reduce blood flow to the brain because you're sleeping? Honestly, no. Your brain gets pretty much the same amount of blood with every beat of the heart, no matter how much blood the heart is beating. So if you speed up your metabolism because you're exercising, you know your heart beats stronger, you know you have higher blood pressure, you know you have more blood flowing, you can actually increase the blood flow to the body by 7 times if you're a well-conditioned athlete. Us couch potatoes, maybe 4 times as much. So if at rest, I'm pumping 5 liters of blood per minute through the heart, then when I'm exercising, I may be beating 20 liters of blood through the heart per minute. It's the same 5 liters that I have in my body. I'm just doing it 4 times a minute instead of just once a minute. Does that make sense to everybody so far? All right, so how much of that does your brain get? It gets about 650 milliliters, 700 milliliters of blood. Out of that 5 liters, less than a liter to your brain, okay? Doesn't matter if you're awake, asleep, dreaming, not dreaming, sitting here listening to me talk, working out, doesn't matter. Your brain gets the same amount of blood. Different parts of your brain get different amounts of blood, and that's the basis of PET scanning. Y'all know what PET scanning is? PET scanning is one of the ways we have of determining which part of the brain is active, and that's based on blood flow within the brain, but the brain as a whole gets the same amount of blood regardless, okay? That will be important next semester when we study the cardiovascular system and how it's regulated. How does that relate to our subject today? Well, what happens when your muscles are more active? You send more blood to the muscles. So the muscles at rest get about 1,200 milliliters. That's 1.2 liters of that 5 liters total that you're sitting there right now, pumping about 5 liters of blood per minute, a little bit more than 1 liter going to your skeletal muscles. Okay? That's quite a high amount, don't you think? Let's see if they're just visiting or if they're hanging around. I'm sorry, y'all didn't even realize we're having a class here, did you?
Oh, sorry.
It's okay. If you can relocate, though, that sure would help.
All right.
Okay, thanks. No idea we were having a class in here. Just found a shady corner to sit in. Happens every once in a while. Okay, well, that will make the recorded lecture more exciting for everyone. Okay, so 1.2 liters of blood flowing to all your skeletal muscles right as you're sitting there right now. What happens when you're exercising? You increase it to 1,200. You increase it by 10 times when you exercise. So what does that tell you about the demands of the muscles' metabolism on your blood flow? It's huge, right? But even for resting values, more than 1/5 of your blood flow at rest is going to your muscles, okay? Now, blood flow to the muscles, we said yesterday, supplies oxygen, it supplies your fuel molecules, and it carries off the wastes, right? That's true of any organ. So what are the main fuel molecules that your muscles require? It's okay to refer back to your notes from yesterday if you need to. You need glucose, and what else? Acetylcholine is not a fuel molecule. A fuel molecule is what you're burning to get the calories to make the ATP. Josh, did you say something else?
No, I was stuck on glycogen.
You were stuck on glycogen. Glycogen is made in the muscles.
Yeah, well, it was the precursor to glucose.
Right.
So it was like stage one.
Okay, so, and that's all fine. You're thinking in the right framework. So if we just look at a picture of a muscle, just to draw a sketch. Here's my muscle fiber. And then I need a blood supply, right? Here's my capillary. What am I supplying? I have got to give my muscles some oxygen, right? So I'm going to bring oxygen. And then in exchange for that, what am I doing? Carbon dioxide out, right? Oh, so we got that. That's pretty straightforward. But my fuel molecules, the organic nutrients that I'm bringing in from my bloodstream, are glucose and fatty acids. Glucose and fatty acids are the monomers. Remember, those are the building blocks of your organics, and they have to be in the monomer state to be able to absorb them across these membranes. So I'm going to absorb fatty acids, and I'm going to take in glucose. Now, I want you to think back to what we learned about cell membranes. Do fatty acids diffuse easily through cell membranes? They're lipids, right? Small lipids can go right through plasma membranes, no problem. Fatty acids are individual little, well, they're not that little, but they're still small enough, okay? Fatty acids, individual fatty acids are small enough to diffuse through plasma membranes. Glucose, though, how does it go? It has to have a carrier. So I'm going to have a carrier for glucose, and that carrier molecule is regulated. And here's the hitch and why we're doing this today. That carrier is regulated by insulin. And there are other things that I take into my cells along with glucose that are also going to have carriers regulated by insulin. And even though we're not using them typically as fuel molecules, they're there. What does AA stand for? Amino acids. And amino acids also, most of them, have to come in by carriers, and those carriers likewise are regulated by insulin. And I want you to remember it even though I'm just laying some groundwork now. This next semester we'll study the effects of insulin and diabetes, and that's why this is important now, okay? So when do you secrete insulin? When you're starving, when your blood sugar's low, or right after a meal when your blood sugar's high? Right after a meal when your blood sugar's high. That high sugar stimulates the cells of the pancreas that secrete insulin. They're called beta cells. So you have the beta cells in the pancreas that secrete insulin when blood sugar's high. And insulin has a permissive effect. What does that mean? It says, yes, you may have some sugar and some amino acids while we're at it, okay? So if you just ate a meal that had some protein and some carbs in it, and you digested that, then as your blood levels of amino acids and sugar rise, the insulin tells the muscle cells, hey, we just ate, you may have some. Okay, does that make sense to everybody? Okay, so to me it's kind of like you just went to the grocery store. What are you going to do when you just went to the store? You're going to eat, right? If you're like me, it's like I'm eating in the car on the, no, it's not that bad. Not that bad. If it were Girl Scout cookies, when the Girl Scout cookie order comes in, I have that delivered to me here. I got a hookup, I do. So I order like 12 boxes of Girl Scout cookies. If I get them home, when they get home, my husband's designated box of Samoa's disappears in one day. It's gone. Josh.
Just in regards to insulin, would diabetic patients they test afterwards, right? About like maybe 30 minutes?
That's probably more than I know. But what happens is it depends on what you ate. So if you eat a Snickers bar and wash it down with a glass of Kool-Aid, you know, you're getting a lot of simple sugar in a hurry, your insulin's going to rise.
You would know how to adjust.
Yeah, so you have to adjust accordingly. Right. I don't eat a lot of simple sugars. I just decided that sodas are evil. Simple starches, likewise, you digest them so fast, your blood sugar tends to spike. White bread, white starches like potatoes and white rice. Yeah. Whole grain things take longer to digest. And so your blood sugar rises more slowly, and that seems to just be better to your overall health. And we have a problem when your blood sugar rises too high too fast. You secrete a lot of insulin and as a result of that, and you secrete so much insulin that your blood sugar then plummets. So if you just eat a lot of sugar at once or a lot of simple starches at once, your blood sugar shoots up, and then the insulin shoots up, and your blood sugar plummets right back down. That's called reactive hypoglycemia, and that's bad. Okay, so what does hypo mean? It's either too high or too low. Which one is it? Hypo is too low, and glyc is glycogen, sugar, and emia is blood. So hypoglycemia is low blood sugar. What does your brain do when your blood sugar drops too low? Can't function. You get sleepy. Go to sleep. You might get the shake. Some people get shaky, feel weak, feel nauseous. But some people just feel sleepy and just go to sleep. And unless you can recover from that, that can be fatal. Okay? So if it's a diabetic who takes too much insulin and trying to adjust their doses, and I've had students come to me and ask for sugar. Yeah, and I always give them the sugar first, and then I ask them, what did you do that you needed sugar? Because their hands are usually shaken by the time I'm handing them packets of sugar. Well, one of them told me once, my daughter's birthday party was yesterday. I was in a hurry this morning. I knew I needed to eat something. There was leftover birthday cake. I knew that wasn't the right thing to eat, but it was all there was, so I ate it anyway, and then I tried to adjust my insulin dose to match the amount of sugar I'd eaten, and I overestimated the insulin, so what happens when you take in too much insulin? Blood sugar drops. So most diabetics that I know carry an emergency pack of crackers, the little glucose drinks, whatever. It's absolutely crucial. So how fast can you die from that? You pass out quickly enough that if you don't have help, you are going to die. And I had one of my very best students ever who was actually watching. She had custody of her grandchild because her daughter and her daughter's husband were both in the military, both serving in Iraq at the time. So she had custody of a 2-year-old, and she was a student of mine and then went over to UT Tyler and died in her car in the parking lot at UT Tyler with her purse open and her sugar, her emergency sugar, in her hand. So she knew she was going to pass out. She knew what was happening, and she just couldn't get the sugar in her fast enough. She couldn't help herself, and no one was there to find her. So how serious is that? Is that serious enough for you guys? Yeah, pass out and die. One of my husband's professors, brilliant woman, had died of hypoglycemia at her desk at the college. Snickers bar in one hand, telephone in the other hand. Didn't make it. So.
We had a class period yet where somebody had died.
You know, I'm not keeping track of those, but I do want to point out, I want to subtitle my course 101 Ways to Do Somebody In, but I'm afraid that's not a good recruitment tool. But since they're almost all recorded, you could go back in time and tally them all and let us know. When you're studying for the final, you could do that.
Every class where somebody doesn't die, but maybe just like 1 or 2.
I just don't know about that. I'll try to meet your needs.
Wait till the next time we meet and be like, okay, so remember how I was teaching you yesterday.
Mm-hmm.
I have 5 stories about people dying.
So I can give them to you, delay them by a day, just to give you a break.
The last day of class will just be death stories.
Yeah, we could do that. I went to a seminar once, a nurse who worked in pathology was giving a talk on causes of death, and it was a summer talk, so it was July 4th weekend or thereabouts, and so her theme was red, white, and blue causes of death. Causes of death from erythema, cyanosis, and pallor. So it was circulatory problems, all of it, but yeah, I don't think I'll do that. So I just try to sprinkle them in there to make sure you're awake. Okay, so where are we getting to with all this? How important is insulin? It's absolutely crucial, and different cells have different reactions to insulin. For example, your liver doesn't need permission to pick up glucose from the blood, picks it up readily, but insulin triggers the storage of glycogen in the liver. What it does in skeletal muscle, though, is it says, suck it in. Just suck as much as you can out of the blood, and once all of that sugar is in the muscle cells, then that triggers the storage of glycogen. Does that make sense so far? So how much muscle tissue do you have in the body compared to, say, brain tissue? If you had to weigh them, which one weighs more? Brain weighs more than all your muscles combined? Not in individual muscles, but all your muscles combined. I would say you have more muscle tissue. And which one gets more of the blood flow? Muscles get roughly twice as much blood flow as the brain. So once you trigger that insulin, how much glucose goes in, or how much glucose goes into your muscles? Quite a bit. So you have to have high glucose to be able to afford to stick glucose in your muscles. Because if glucose levels are low and your muscles are still absorbing glucose, then your brain's going to starve. And you're going to pass out and potentially die. Right? So, go ahead. I remember telling you guys I was auditorially distracted, but that's okay. I know I'll get back on track here in just a second. It's going to just take me a second, though. Okay, so then I like to divide the metabolism of muscles into really 4 different stages. So you're going to be at rest, or you're going to be active. And there are 2 stages at rest. You can be what we call the absorptive stage, which means you just ate. Or you can be post-absorptive. And technically, and we'll worry about this more next semester, technically there's 2 stages of post-absorptive. Did you eat recently, or are you starving yourself, basically? Okay, but we'll worry about those details later because they have more to do with the liver than they do with the muscle. And obviously with muscle, activity matters. So what were our 2 kinds of activity? Aerobic and anaerobic. So does it make sense to you that muscle metabolism is going to kind of shift gears, depending? So if you're in the absorptive state, is your glucose level high or low? Absorptive means you just ate. It's pretty high. So are you secreting insulin? Yes. So are the muscles getting fed glucose from the bloodstream? Yes. What are they doing with most of that glucose? Remember, they're at rest. Storing most of it. They'll burn, if glucose happens to get snagged by one of the enzymes of glycolysis, it'll get broken down, but it's much more likely that there's so much glucose in there that more of it will get stored, stockpiled away. This is like taking your groceries home and putting them in the pantry or the freezer or the fridge. Okay, so store them away for later. If you're in the post-absorptive stage, then your glucose is low. And I don't mean low like dangerously low. I mean it's just lower than, the median point. So are you secreting insulin or not? Shouldn't be. Okay? So are you taking glucose into your muscles? No, you're not. But are they going to use their glycogen reserves? No, they're not. Okay, and this is the part that most people just sort of go, what? And the reason is that the other thing you have is your fatty acid reserves. Okay? So you don't have to burn your glycogen, which you've stockpiled, when you're at rest. You have fatty acids in the blood pretty much all the time. They just sort of hit a steady state. There are different sources of them. We'll worry about that next semester. But yeah, you have a fatty acid level, so you're feeding your resting muscles fatty acids. Yes?
So if your body needs to, would it fuel like from your fat cells to get fatty acids to fuel out from the,
Yes.
and then like I guess if like you're starving, would you use insulin? Well, it wouldn't need insulin.
You don't secrete insulin unless you've eaten, right?
Right.
So we have other hormones that are going to balance that. But
Well, I was just thinking like fatty acids to be absorbed, but they can be special. Glycogen or glucose is only needs insulin to be able to go in. So
glucose and the amino acids.
that was just me.
Okay, so yeah, I'm trying to stretch the walls of your parameters, so I hope it sounds like I'm doing a good job. Okay, so you feed your muscles fatty acids pretty much all the time. So are there fatty acids over here in the absorptive state? Yeah, they're just there. So a certain level of your metabolism in your muscles is going to just get the ATP it needs from fatty acid breakdown. Fatty acids, by the way, are broken down in the mitochondria, and I don't know if I ever finished that story. So if this is a mitochondrion, you remember we had 2 steps? We had the Krebs cycle. And what we did here was take pyruvic acid in and convert it to acetyl-CoA. Does anybody remember that? Okay. So fatty acids can also be converted to acetyl-CoA. So they just feed right into Krebs cycle. Mitochondria don't know the difference. Okay? They don't care if they don't ask that acetyl-CoA, did you come from glucose or are you from a fatty acid? It's just all the same. So to your cellular metabolism, fatty acids are great, and they just diffuse right through membranes, and you just tend to have a normal level of them in the bloodstream. If you just ate, they're coming from your diet. If you're in the post-absorptive state, then you are going to pick them up from your fat reserves or from your liver. Your liver stores fat. Or your muscle cells, some of them, remember, will store fat as well. Okay, so if you're in the absorptive state at rest, you burn fatty acids and you stockpile the glucose as glycogen. Does that make sense? If you're in the post-absorptive state, you're not stockpiling any glucose right now, but neither are you using up your stockpile. You're just going to burn fatty acids. Okay, if glucose is available, and I imagine there may be some, it's going to get broken down. But for the most part, post-absorptive, your muscles are burning fatty acids. So if you exercise regularly, you can help maintain a normal body weight by doing weightlifting exercises. How does that help? What does weightlifting do to your muscles? It bulks them up. You don't want to overdo that. I was looking at some pictures yesterday. Oh my gosh. You don't want to overdo it, but the bigger your muscles are, the more their resting metabolism is. The more fatty acids it takes to maintain your normal resting metabolism, and so the more you get to eat and not worry about gaining weight. Okay? Just don't overdo it. All right, so does everybody see at rest? We burn fatty acids. That maintains the needs of our muscle cells when they're not active. And the difference between absorptive and post-absorptive is, am I storing glycogen right now or am I not storing glycogen right now? Okay, when am I going to use that glycogen? So I'm going to use my glycogen mostly when I'm in the anaerobic state. But depending on how long I stay in the aerobic state, I can break it down there as well. So I'm going to take my glycogen reserves, and in the case of the aerobic state, I'm going to break it down to CO2 and water. What am I going to do in the anaerobic state? What do I break it down to? Well, the ATP is a given. We need ATP. What's the waste product? Lactic acid or lactate. Okay, so that's a huge difference, isn't it? I either break it down completely to CO2 and water, which means I've extracted all the energy out of it that I can, or you remember the analogy I gave you yesterday, it's like taking one bite out of the cookie and throwing the rest away. Lactate is the rest of the cookie. And so lactic acid is throwing energy out of the muscle cell. It's not eliminating it from the body, it's just getting it out of the muscle cell so that the muscle can continue to break down glycogen. Okay? Which one can you do for a long period of time? Aerobic. As long as you supply oxygen to your muscles, you're going to keep going until what? Until you run out of, and you also have fat reserves as well that you can use. Fats can only be broken down aerobically. You cannot burn fat doing anaerobic exercise. So if you're doing prolonged aerobic activity like running a marathon, that's pretty long, right? 26 point something miles. So what causes people not to be able to finish a marathon? If they run out of fuel, it's like when your car runs out of gas, no amount of wishing is going to make it go. So if you run out of fuel when you're running a marathon, your muscle cells have literally run out of glycogen, run out of your fat reserves, and I don't know of many marathon runners that actually have a lot of fat reserves. They generally are very lean. So they're running on glycogen reserves. So what do most marathon events have the night before, the day before the big run? They have a carb-loading dinner, pasta dinner or whatever. And what they're trying to do is fill up your glycogen reserves in your muscles the night before the big race. But I have seen video of people who almost within reach of the finish line, sat down and could not take one step further. Are completely out of gas, and no amount of willpower is going to make those muscles go if you've run out of fuel. Okay, so I mean, it can happen. Most of us don't push ourselves that far, but it can happen. And I don't know about y'all, but that's on my. I have another 101 list. It's my 101 flimsy excuses not to diet list. You know, I don't want to run out of glycogen. That would be bad. So. Okay, so does everybody appreciate muscle metabolism in the larger realm of what's your body's state of activity? What are you doing? What do you need? What are your fuel reserves? And then there's one other thing I should mention here, just because Josh brought up his objection to how to do somebody in. Cyanide poisoning. How does cyanide work? Anybody know? It works in the mitochondria by preventing the electron transport system. It just stops it cold. Stops it cold. So you can't make ATP aerobically. And remember, your muscle cells are the only ones that can do this anaerobic thing without oxygen. So what happens to your brain cells? They die. They just die. So, and it's not a pretty death. I don't know if you've ever seen in the movies when someone swallows a cyanide pill. They foam at the mouth and they have seizures. Yeah, because what your brain cells are doing individually is they're swelling and bursting. I think the foaming is due to the electronic activity of the brain as the cells swell and burst, but honestly, I'm not entirely sure. And I don't know of a polite way to do a Google search without the FBI worrying about me, so I'm not going to look that one up. You can ask the pharmacist at work if he or she knows. They might look at you, you might, yeah, we don't want you losing your job over asking suspicious questions, so let's just don't go there. You know, hypothetically, how does cyanide work? Okay, so I like to put this all in the huge frame of metabolism. We've hit metabolism twice this semester already. We did it with the cell chapter very briefly. We've done it again now. We probably ought to do it with neurons, but honestly, we probably won't have time. That's just next week. So let me just tell you now, I've told you twice already, brain cells die if they don't get oxygen. They just die. And then next semester, we spend a whole chapter on digestion, nutrition, and metabolism. So we'll hit it again then. But the better you have kind of that big picture idea of what's happening in your cells, the better off you are. Okay? So respect your mitochondria. And if you look at that in terms of how many mitochondria do your cells have, I think I mentioned this once, but it bears repeating. When you look at those generalized pictures of a cell, like back in chapter 4 when they have the pictures of all the organelles, they might have 5 or 6 mitochondria in the cell. I'm going to tell you the low end of mitochondrial count per cell for just a typical cell is 300 mitochondria. And remember, each mitochondria is about the size of a bacterial cell. 300 is low. Liver cells have like 1,000. Yeah.
The more active you are, don't some cells produce more mitochondria to like
Well, actually, we're going to talk about that because there are other things that muscles do when you condition them. So aerobic conditioning can increase the size of the individual cells, and concomitant with that, you do get more mitochondria. Mitochondria, remember, reproduce themselves. They divide like little bacteria. They just go through cell division, and so you're producing new mitochondria in your cells pretty much all the time. But if you goose up your metabolism by increasing your aerobic exercise, then the muscle cells hypertrophy, they get bigger, and they produce more mitochondria. So we're looking at muscle cells, and remember, these are muscle fibers, so they're huge to begin with. They are going to have thousands of mitochondria in them. So don't think of mitochondria as just sort of being scattered hither and yon. In fact, let me see if I can find that picture of the cell we were looking at before, because when we looked at that picture, we didn't really look at the mitochondria. Not that one, not that one, no. Nope, they leave them out of that picture. That's not very nice. Not great, but it may be all that we get. So do you see mitochondria in this picture? I see 3. How many should there be? Wherever you see a mitochondrion in that picture, you see where it is? It's kind of in between the myofibrils. They are just going to be crammed in there. And in the longitudinal view, let's see if I have that. Nope, not there, not there, there. See mitochondria here? How did I do that? What did I do? So mitochondria is labeled there. But in fact, you see where that nucleus is, that big purple nucleus right there? Where you're going to find your mitochondria are just lined up between the myofibrils, just end to end. Just a whole line of them. So I think they have the size right, but they just don't have the number anywhere close to right. Okay, so it's really important for you to have a good sense of what your muscle metabolism is doing. And that brings us to the next big topic that I want to go through, which I've already mentioned once, and that's the different kinds of muscle fibers. And you remember yesterday I said some are red and some are white. Do you remember what it was that made them red? Myoglobin, very good. And the fact that they tend to have more mitochondria So we classify the muscle fibers into these technically 3 types. Type 1, type 2 are the main 2 types. And let's just cut to the chase and look at the picture. Why do they always put the pictures at the end? There we go. So you can actually see the differences when you look at them under the microscope. And the red fibers are darker in color, and the white fibers are lighter in color, this is not the greatest picture of them, but in general, the white fibers are larger. They're longer and they're bigger around. Red fibers tend to be smaller. So the proper names for these are fast twitch and slow twitch. Slow twitch is red. Fast twitch is white. But you notice some are kind of in between color-wise? So those are also fast twitch. So we have 2 kinds of fast twitch. And we used to call the one kind intermediate twitch. I don't know why we didn't just call it pink, but we didn't. So, and in fact, genetically, the slow fibers and the fast fibers cannot convert. So you're born with a certain mix of slow and fast fibers in different muscles in your body. And you can, with training, convert the fast twitch from the one form to the other. So if you do a lot of aerobic training, you want to run marathons, a lot of your fast white fibers will become fast intermediate pink fibers. You can add more myoglobin into them. They can build more mitochondria in them. But you cannot convert slow twitch fibers into fast twitch fibers. So if you're a competitive athlete and you want to be good at whatever you're born to do, people actually have muscle biopsies done to see what the mix of slow and fast twitch fibers are, and then train accordingly. If you have a lot of slow twitch fibers, then you're going to be better at a marathon. If you have a lot of fast twitch fibers, you're going to be a sprinter. So it makes a difference. Okay? So what I want to do is go back to our theme of form and function. What does it look like? How is it built that lets you understand why the fiber types are what they are? So to do that, we need to look at some of these variations. And we're going to start with just that list of the 3. So our first type is the SO, the slow oxidative. These are called the type 1s. And as the name tells you, they are slower. They're not slow. They're just slower than the fast ones. And they're going to be better for your aerobic respiration. So are they going to have more or less myoglobin? What does myoglobin do for you? Provides oxygen. So do I need that for aerobic? Yes. So do I want more of it in these slow guys? Yes, because they're good for aerobic. Okay, so I'm going to have more mitochondria. I'm going to have more myoglobin in my slow twitch fibers. Okay? So that's the slow the name oxidative tells you they're depending on, for ATP production, on oxidative phosphorylation. All right, our intermediate, type 2A. These are fast, but they're oxidative. So calling them oxidative means they rely on aerobic respiration. So they're fast because of the combination of the kind of ATPase they have, the amount of myoglobin they have is not as much as the slow ones, but it's still more than the white ones. Okay, so FO, fast, oxidative, or type 2A fibers. They're the fast kind, but they're not as fast as type 2B. These are the glycolytic fibers. So they're depending on glycolysis, and that means taking a bite out of the cookie and throwing the rest away. Taking the glycogen, breaking it to glucose, taking that first step of glycolysis to get just a little bit of ATP and throwing that lactic acid away. Just throw it away, it's faster. Are they doing some aerobic respiration? Yeah, but their demand for ATP is so great that the mitochondria can't keep up. And so as the pyruvic acid builds up from its rapid breakdown, the excess gets converted to lactic acid and thrown away from the muscle. It's not a waste product to the body, it's just not usable by the muscle. How long can you do that? Not as long as you can do aerobic. You're going to either run out of glycogen or the lactic acid's going to build up so fast that it retards the glycolytic pathways. Okay? And they don't have a lot of myoglobin, and that's why they look white. And because they're not as reliant on mitochondria, they don't have as many mitochondria. What they do have, that a lot of the books, including this one, do not mention, is they have more sarcoplasmic reticulum than the other guys. So what does that give them? If they have more SR, what do they get out of that? What does the SR do? It's okay to look stuff up. It does three things to our favorite ion in muscle, which is what? Calcium. So what are they doing? What's the SR doing? It stores it. It releases it when you want contraction to occur, and it picks it back up to restore it so that relaxation can occur. And the more membrane you have, the faster it can do that, and the more calcium it can store. So these large fibers, because they're large, they have more power, and because they're large, they can move a heavier load. So you're going to get more locomotion faster from white ones. But unfortunately, they also fatigue sooner. They hit muscle fatigue sooner. The lactic acid builds up, the depletion of oxygen takes its toll. You build up an oxygen debt, and you run out of steam. Okay? So depending on your conditioning, if you're an athlete and you're going through conditioning for one kind of a race or another, then you train for a sprint or you train for a marathon, and that then builds up the size of the muscle fibers and the degree of the combination of the type 2B and the type 2A, because remember, those can be interconverted. Okay, if you're still having trouble imagining this, then I want you to imagine animals that, unlike humans, don't have such a mix of fibers. Almost all of our fibers are a good mix of the slow and the fast. So we don't have too many individual muscles that are all slow or all fast. I would say if I had to pick some, it would be the muscles that move your eye. Do you think they're slow or fast? They're very fast, right? It gives you good visual tracking capability. But if you ever sat and just tried to move your eyes rapidly, they fatigue fairly quickly. Now, you don't have to practice that right now. But there are other animals who do have specialization. So, for example, in some birds, they're specialized for long-distance flight, and other birds that are specialized for rapid bursts of flight. So let's talk about that. So do you know any birds that migrate over long distances? Geese do. What else? Ducks do. Lots of shorebirds do, but we tend not to look at their anatomy too much. But has anybody ever eaten duck? What's the breast meat of a duck? Is it dark meat or white meat? It's dark. Okay. Whereas, as we all know, chickens and turkeys, breast meat is white meat, right? Chickens and turkeys are ground-dwelling, forest-adapted birds. And like most of the fowl, the kinds of birds that live on the ground, if you can coerce them into flying, how far do they fly? Just far enough to get out of your reach, to go up and then disappear back into the ground cover. Okay, so very fast but short, rapid bursts of flying. So does everybody see the difference between the red fibers, like you find in migrating birds, it would not do to fatigue halfway across the Gulf of Mexico, right? That would be bad. Okay? Versus the chickens and other ground-dwelling birds, which just need to go hide in a different spot. Okay? So where do you look for dark meat on chickens and turkeys? The thighs and the legs, because they walk. That's what they do. They don't walk that much, maybe, but those legs are made for walking. All right, any questions about the different kinds of fibers? I believe you have in your book a table that contrasts them and some questions in your practice quiz on how to tell them apart. Okay, so we've been talking for about a day and a half about individual muscle fibers, and now we want to build that back up into a whole muscle. We started with a whole muscle. We started with the anatomy of a whole muscle. And then we went down to the microscopic anatomy of individual fibers, and then we did the physiology of individual fibers, and now we're building it back up into a whole muscle. So as we do this, recall what you learned in lab yesterday. Okay, so if I stimulate a muscle to contract and I get one contraction out of it, what do I call that? That's a twitch. Okay, so if I provide a stimulus and I get a single contraction, that's a twitch. The amount of force that's generated by the muscle is called its tension. And I want you to think about this. This is going to make a lot of sense to you once I put it in words. The amount of tension that's generated by a muscle has to exceed the weight or the mass of the load that it wants to move. If I have a 10 gram weight in my hand, that's not much. Okay, so if I have a weight in my hand, how much force am I generating by my muscles just to hold my hand? The force I'm generating is exactly equal to the load it's carrying. If it's less than the load, then what happens? It's going to fall. If it's more than the load, what's going to happen? It's going to continue to contract. Okay? So that, to me, is very straightforward. If you know what the load is, then that's a measure of what the tension is. If the tension is equal to the load, then you're just holding it against gravity. If it's greater than the load, then you're moving it. Okay? So have you ever picked up something that was lighter than you thought it was going to be? So what happens when you do that? You want to pick up a bucket you think is full and it goes, woo! Yeah, because your brain is calculating how much force do I need my muscles to generate to carry that load. And, you know, with practice you get pretty good at it, but if you don't know how much it is, then it can cause problems. Okay, have you ever done the opposite? Yeah. Tried to pick up something that you turned out to be heavier than you thought?
This book.
Yeah, that book's a good one. Good for your exercise. Yeah, I was helping my husband when we were moving. He was clearing out his workshop, and he had everything stored in pickle buckets. Because, you know, it's a good way to store it. So I'm moving one pickle bucket after another with the lids on them because I don't want to know what's in them. I just don't want to know. And I went to pick up one, and it just didn't even budge, and it turned out it was full of lead weights. Of course, because you never know when you're going to need a lot of lead weights. Okay, so you get the idea of tension and force. In lab, I'm sorry to say, I don't know what video you watched. I was going to ask Ms. V to share the link with me, and I forgot. So, so what did you see? You saw an animation or anything? Nothing? Oh, wow. Okay. So let's just go through the classic physiology experiment on muscle contraction, because you would be culturally bereft if I didn't do this for you. So, so what we do with y'all in lab when the stimulator box is working is we zap your muscles and let you see what happens. But if you were in a classic physiology class, then you would be dissecting a frog. And we don't do this very often anymore, mostly because we're worried about frog populations worldwide. Has nothing to do with our concern over your sensibilities, trust me on that. So we pith the frog. What does that mean, to pith a frog? You don't know what it means to pith a frog? So you'll be glad we don't do this anymore. It was not ever my favorite part. I like frogs. To pith a frog, you grab it, you force its head kind of flexed forward, and you stick a dissecting needle down its spinal cord and up into its brain. So you go down the spinal cord and up in the brain, and you're scrambling the brain. You're doing this if you're doing it right, you're doing it very quickly, and the frog has a moment of distress for having been grabbed, and then it feels nothing. But the body is still alive. The heart is still pumping, and you can study live muscle physiology. And what you do next, of course, is that you have to dissect away the skin of the leg. We use the gastrocnemius muscle. It's a nice muscle to use because it's got that nice Achilles tendon on it. So here's the gastroc muscle. We leave it attached at the knee, and we're going to attach it to a contraption with a hook, and that hook is going to attach to a lever, and that lever is going to have a fulcrum point, and at the other end of the fulcrum is going to be a marking device of some kind. And that marking device then is going to write on a piece of paper or something. The old-fashioned way is to put it on a big drum that rotated, and so you would just put a piece of paper around the outside of the drum, and as the drum rolled, then while you're making the muscles twitch, the line on the paper is being moved. Okay? It's all computerized these days, but that's the old-fashioned way to do it. All right, so if I need some stimulators, right? So I have my electrodes hooked up to my muscle, and my electrodes are hooked up to my stimulator box so that when I push the little button, an electrical current runs through the muscle, and that makes the muscle contract. Are you with me on that? Okay. I go to this much trouble because you have to understand why the graphs look the way they do. Okay, so when that muscle contracts, what's it going to do? It's going to shorten, right? And when it does, what is that going to do to my hook? Raise it or lower it? It's going to pull it down because the hook, remember, is attached to that tendon. This is why I go through this, because I want you to be able to visualize this. What does that do to my pen? The pen, of course, is going to go up. Does that make sense to everybody? Got it? Okay, so what does the graph look like then when I contract the muscle and then relax it? It goes up, and then the muscle relaxes, and it comes down. And that's why muscle twitch looks the way it does. Okay, you're actually graphing the amount of tension being generated as that muscle contracts, and then relaxes. Okay? All right, so the next thing is to pay attention to when we stimulated the muscle. We actually stimulated the muscle before it started to contract. So we have this period here, very short period, of about a millisecond. And then the muscle starts to shorten. What's happening during that millisecond? What's happening inside the muscle? This is what we call the latent period. You stimulated it, but it hasn't responded yet. So imagine those individual muscle fibers. You remember that electrical current opens voltage gates, right? So we're hitting it with a threshold or super threshold stimulus enough to open the gates. And as the gates of the muscle fibers open, then that stimulus runs down the T-tubules, opens the calcium voltage gate, calcium is released, calcium binds to the troponin tropomyosin, actin-myosin start to pull. But remember, they have to pull on the tendons. And so it's kind of like pulling a slack rope. You have to tighten the rope before it can pull on the muscle. So if you get just a threshold stimulus, then you might see the muscle tighten and then relax without moving the load much. Okay? If you get a stronger than normal stimulus or stronger than threshold stimulus, then you release more calcium, you get a stronger contraction, it stays loose longer because there's more of it, you get a stronger contraction, it pulls before it relaxes. Okay, so you need to, and you can go through your text materials, you need to know what's happening in the cells during the latent period. What do we call the period after the latent period? That's just the period of contraction, the period of relaxation. Okay, so during contraction, calcium is loose, myosin and actin are sliding together. At the peak of contraction, they're slid together as much as they're going to. And during relaxation, you're putting the calcium back into storage. That should all make sense based on what we learned yesterday. Okay, so what did you learn in lab yesterday will happen if I stimulate the muscle not once but twice. I'm going to stimulate it. It's going to start to contract. So here's my latent period. And if, while it's contracting, what if I stimulate it again? What happens? Depending on whether I do it too soon or not, I can get a second contraction on top of the first one. What did we call that? Summation. We just add together the effects of the two. What kind of summation? Temporal. Meaning over time. So if I zap it repeatedly, then what? What if I just hit it one time after another, after another, after another, and speed up the frequency with which I'm hitting my muscle? What's it going to do? It starts out by contracting. Can't relax completely, so the second contraction is higher. Can't relax completely. And then complete tetany. Tetany is the fusion of twitches. So we go from temporal summation to incomplete tetany to complete tetany. So how does this relate to what's happening in your body under normal circumstances? Are you usually a twitchy person? Most of us are not twitchy. Okay, so if you get a tick, facial twitch, you know what a twitch is. Our muscles don't contract like that. Our muscles contract smoothly, and we can sustain contractions. We do tetany all the time. Tetany is not a bad thing, it's a normal thing. Okay? Make sense? Now, that's very different from muscle tone. So what's muscle tone? You need to know what tone in general is because we're going to use this term a lot. Tone or tonic means continuous, chronic, low-level stimulation. I'm just stimulating my muscles all the time. I got muscle tone. Okay? The only way to completely eradicate muscle tone is to kill the nerve. Do not practice this at home. So if you have someone who's paralyzed, spinal cord trauma causing paralysis, or accidental ligation of a nerve, you just cut it. I have a friend that had that. She didn't die. Just saying this up front. But she had a tumor. She had one of those nervous system tumors I told you about, where she had the cafe au lait birthmarks and a tumor. And when they removed the tumor, they had to destroy part of the root of the facial nerve. What do you think your facial nerve does? You're going to learn it in lab next week, in lecture next week. Facial nerve for facial expression. Okay, so she had, just on one side, the facial nerve was lost. Okay, so immediately she has very little facial expression. It even affected the glands on that side, salivary glands included, tear glands, lacrimal glands included. So she just lost nerve control. But it also caused the muscles to actually atrophy. So when you look at her, you can tell. Even her trapezius, your trapezius gives a nice slope to your neck, not on her. On that one side is just very bony. Because eventually the muscles will atrophy because they have no nerve impulses. But if you just cut a nerve, then you've caused, remember the term is flaccid, they go completely limp. And our muscles are not limp because we have muscle tone. And we have muscle tone because we have chronic, continual, low-level stimulation of our muscles by our nerves all the time. Every single muscle fiber in your body is part of a motor unit. And every motor unit has a motor neuron, either in the spinal cord or in the brainstem. And every motor neuron is, every once in a while, sending a signal out. And they take turns. Remember, the motor units are scattered throughout a muscle. So if you have 1,000 motor units in a medium-sized muscle like the biceps brachii, then at any moment, just a few of them are getting the signal to contract. So as one motor unit contracts, the one that was just contracting relaxes, and they take turns. And so there's no fatigue involved because their turn comes around, maybe once a minute or whatever. I have honestly no idea how often. Okay? So that's muscle tone. And expand on that a little bit and you get the idea of postural muscles. So is it hard for you to keep your head up all day? Is that a challenge? For some of us more than others, I'm pretty sure. But part of it is the way our head is balanced on our spinal cord or our vertebral column, but part of it is the way the muscles of posture are wired by your brain. They do, like muscle tone, only give it a little more power, so it keeps your back up, okay? The muscle, the levator palpebrae superioris, that keeps your eyelid open, doesn't fatigue. When you get sleepy and you can't keep your eyes open, it's not because the muscle was fatigued. It's because the nerve signals are being disrupted by the center in your brain that makes you sleepy. So it has nothing to do with muscle fatigue, okay? So you have this idea of kind of time sharing these motor units so that they take turns. And the term for that, I think the best term for that is to say that they have asynchronous contraction. They contract asynchronously. As one relaxes, another one's contracting. As it relaxes, another set are contracting. And it's so smooth that you can't feel it. You don't feel twitchy. Okay, so far? Are we good with that idea? Well, individual motor units, not individual fibers. Each fiber is part of a motor unit. All right, not all muscles are wired the same. So if I tried to contract my deltoid and keep my arm abducted, are those muscle fibers in asynchronous motor units? Can I hold my arm out all day the same way I hold my back straight all day? Wired differently. Okay, so when I'm doing abduction with my deltoid, contraction of the deltoid, then I am continuously stimulating the same motor units, and eventually they're going to fatigue. And that's different from what I do with my postural muscles, which is let them take turns, wired differently, so that they'll take turns and not fatigue. Everybody see how fundamental that difference is? Okay, did you study motor unit recruitment in lab? How do you do that? We talked about it already, I'm just applying a term. If I need a stronger contraction, then I'm going to stimulate more of my motor units. I'm going to recruit more motor units. So if I need to hold something really tightly in my hand, I give a full strength contraction, whereas if I'm holding an egg in my hand, I'm just not using as many motor units, okay? In lab, you did that by increasing the voltage. Well, if you had done the lab, you would have done it by increasing the voltage. In your body, you do it by simply willfully recruiting. In your brain, you have control over that. And we'll study the brain aspect of this next week. Okay, so did you look at a graph that looks like this in lab? Yeah. All right, so what do we see here? This is the graph of recruitment of multiple motor units. What am I changing in this graph? The voltage. By increasing the voltage. And if you can imagine, if we got to zap you in lab, what we would have done is taken 2 electrodes with a little bit of conducting gel, smeared the gel on your skin, and what we usually do is put a plate electrode on the back of your hand, and we have a needle electrode, which we do not pierce your skin with, up on the elbow somewhere on this thin skin where the nerves are right up under there. You have at least a couple of nerves that we can hit. The median nerve runs right down the midline of the forearm. Does that make sense? Median nerve's going to run there, the ulnar nerve here, and the radial nerve here. So we can kind of usually hit ulnar or median nerve, and that'll make the fingers flex, which is nice for observational purposes. So what would happen if I cranked the voltage knob from, say, 3 volts up to 8 volts? What happens to those fingers? They're not going faster. I would have to increase the frequency to do that. They're just contracting with more strength. Does everybody see the difference there? Okay, so recruitment means increasing the number of motor units and therefore the force of contraction. Got it? So when you see this graph on your lab test, how do you know when you've hit maximum? What is maximum voltage there? 6 is maximum, right? Because right after I hit 6, it went up as high as it goes. How did I know 6 was maximum? I had to go to 7 to see that 7 didn't go any higher than 6. Does everybody understand the logic of that? Okay? How many motor units am I recruiting once I hit maximum voltage? All of them. Okay? What is 2 in this picture? 2 volts is threshold. How do I know 2 volts is threshold? Because I got a contraction after I zapped it with 2 volts. What is 1 volt? Sub-threshold, because when I stimulated it at 1 volt, I got no response. Okay? So y'all have a pretty good grip on that, seems like. Y'all don't mind if we go over lab stuff, right? Okay, so what difference does frequency make? What do we get when we increase the frequency of contraction? We get faster contraction. Now this, what you're seeing here, is something called TREPA. You see that term? TREPA is sometimes called the staircase effect. Can you see why? What's the difference between this and, let's look at a picture of temporal summation. What's the difference between temporal summation here and TREPA, which look like this? Did it go all the way back down to the baseline before you restimulated it? That's the question. Okay, in incomplete tetany or wave summation, no, it did not. But in TREPA, yes, it did. We'll look at the picture again. Do you see how every time it contracts, it relaxes completely before I contract it again? So I'm letting the muscles relax completely. What's making it contract more strongly? That is what TREPA is. It's the increase in strength of contraction when you re-stimulate it after you've let it relax completely. Why does it do that? Athletes take advantage of this when they do warm-ups before a competition. They're trying to warm up their muscles. What difference does warming up your muscles do? Okay, so it increases the blood supply. It increases the temperature, right? And we know that ions flow faster at a higher temperature. So calcium can flow into the muscles faster, and you can get a stronger contraction. That's really all that we can figure out, is that because your muscles are warmed up, you're getting all the calcium released more efficiently. And everything just works faster. All right, so does everybody understand muscle tone, muscle twitch, TREPA, tetany, wave summation, recruitment? It's just a bunch of terminology for ideas, and you just have to know to associate the right concept or category with the right graph. All right, how about the difference between isotonic and isometric? What's the difference there? What does iso mean? Same or equal. Tonic refers to pressure, metric refers to length. So isometric means the muscle is not shortening. It's staying the same length. So I'm going to do one. Y'all can watch if you want. I'm doing isometric contractions of my biceps brachii. Can you tell? Can't tell? Seriously? All right, now I'm going to do an isotonic contraction. So does the muscle shorten when I do isometric contraction? Isometric, same length. It doesn't shorten. All right? Muscles get tense. Why is it not shortening? It's magic. What am I doing when I do isometric contractions of my biceps? What else am I doing? Do it yourselves and you can feel it. You're also doing isometrics of your triceps. Remember, that's the antagonist? So if I contract them both equally, they're both pulling in opposite directions with the same amount of force on the same leg. Okay? Do they do any good for exercise? Is isometric exercise good for your muscles? Hey, it's exercise. Maybe not as much because you're not moving as much of the load, but it's still some exercise. Okay, so what's isotonic then? That's where the load moves. And we have 2 kinds of isotonic. They're up on the screen. Concentric and eccentric. These are dumb terms. I'm going to try to make them make sense to you so you can keep them straight. What does eccentric mean to you? Just in general terms. Strange, weird. Everybody has an eccentric uncle or grandparent, right? Yeah, my brother is the eccentric uncle in my family. He's just kind of a strange little man. Okay, so eccentric, weird or strange. So for muscles, that means weird and different. So what are muscles supposed to do? Pull with force and shorten. So here I am going to do an eccentric exercise. Are you watching? What is my biceps brachii doing? It's lengthening with force. How does it do that? That's weird. So it's eccentric. Okay, so what am I not doing? I'm not just dropping the weight. Okay? So if I prevent the weight from dropping, am I not having to contract my biceps to keep it from just falling? So anytime you set something down carefully, you're doing eccentric exercise. You're lengthening the muscle, but you're fighting the effects of gravity, so you're putting force into contracting the muscle rather than just letting the weight fall. Does everybody see how weird that is? That's eccentric. So what's the opposite of eccentric? Concentric. Okay, so when you do concentric, if you can imagine it, you're drawing a circle. Okay, so a pen in my hand, I am drawing a circle. That's concentric. If that makes sense to you. That has nothing to do with why they call it that. Honestly, I don't know why they call it that. Like I said, dumb terms. Dumb terms to me are dumb if I don't understand why they make sense. They had to make sense to somebody, they just don't to me. Okay, so isometric contraction and blood pressure. This may be a problem, not so much shoveling snow in this area, but you never know. If you're moving heavy weights, what are you doing? Usually you're holding your breath and you're straining your abdomen to keep your back from giving out on you. So if you're lifting heavy boxes and moving them, then you may have problems with your blood pressure. Never mind, your back may give out. That's a totally different category problem. So this is kind of a weird little clinical problem that sustained isometric contractions can cause an increase in blood pressure. And typically it's going to be from moving weights in a way that causes you to contract your abdominal muscles, because that increases the pressure in the abdominal cavity. Okay, this is the last little weird glitchy thing I think I'm going to have to deal with. I sure hope so. It's the length tension curve. And I'm going to show you the picture first and try to make sense of it for you. And I'm not going to put the graph on the test. Okay? But we're going to apply this again next semester with the heart. So if it makes sense to you now, it will help you next semester. Remember, the heart is also striated muscle. So what's true of skeletal muscle is true of striated muscle. So what we're looking at here, again, is our thin and thick filaments slid together. Look at the far left. When they're completely contracted, can they shorten any more than they're already shortened? No. So how much force can I generate from this position? None. So notice that between 1 and 1.5, the amount of tension is 0. The amount of more shortening I can do is 0. This sounds nonsensical. It's just a theoretical thing. What if my filaments were already slid together as close as I could get them? Could I shorten them any more? No. So it's just kind of a logical thing. Now, look at the far right. What do you see? They're stretched out so far, there's no overlap. Myosin heads can't reach the actin at all. How much force can they generate? None. Because they can't reach. They're completely slid apart. Okay, so if the myosin heads cannot reach the actin, then they can't attach. If they can't attach, they can't pull. If they can't pull, they can't generate any force. So between 3.5 and 4, that's how stretched out it is. How much force are we generating? 0. Does everybody see the 2 0 points on the ends of our graph? So now look for the high point. What do you see? It's called the resting length. And you'll notice that almost every myosin head overlaps a thin filament. So every head has an actin in reach, maximum amount of overlap. Does everybody understand the optimum length? Okay with that? Now, what we'll see next semester is that in the heart, it's a little closer at rest. So look up here for another one of my handy high-tech demos.
In skeletal muscle, we overlap them optimally at rest because the default position of your skeletal muscle is rest until I need you. And when I need you, be ready. So at rest, you're optimal. In the heart, rest is a little closer together than optimal. Because in the heart at rest, I don't need my strongest contraction. When do I need my strongest contraction? Am I resting or am I exercising? Exercising. How much blood do I have coming back to the heart when I'm exercising? More, right? What does that do to the heart? Stretches it. And so by stretching it out only with increased activity, I hit optimum only when I need a stronger contraction. Make sense? If it makes sense for now, I'm good. Okay? Planting the seed for next semester, because next semester what you're going to find is if you just stretch the heart passively, you just pull on it, then it contracts more strongly, and you already know why. Okay? Questions about that? That was the linked tension curve. All right, fatigue. What's going to cause fatigue? How do you know when you're fatigued? So most of you undergo what we call psychological fatigue. What does that mean? Your brain is tired of running before your muscles have given out. Okay, so when we talk about muscle fatigue, we're literally talking about running out of something. And it's the same with nerve fatigue. You actually can have neuronal fatigue. We'll study that next week. But the basic idea is the same. If I run out of something I need to keep going, then that's when fatigue hits. In the case of muscle, depends on what kind of exercise you're doing, but it could be, as we said, you're running out of glycogen. It could be that you depleted your oxygen reserves. It could be that you have too much lactic acid built up. Okay? It's probably not going to be that the nerve ran out of anything, because the muscle's going to run out of stuff before the nerve does. The nerve can recover faster than the muscle can recover. So muscular fatigue is generally caused by depletion of either the fuel molecules, that's the glycogen, glucose, fatty acids, or the oxygen. And when you get fatigued, then you can suffer from oxygen debt. Okay? Now, your book mentions some other things, lower calcium and stuff like that, but generally, I don't know how much that actually affects it. Okay, we've talked about hypertrophy, right? What did that mean? Not too much. Hypertrophy is growth in the size. How is that different from hyperplasia? In the number of cells. So if I increase the number of cells by cell division, I get to do hyperplasia. Okay, hypertrophy means the individual cells are getting bigger. So which one am I doing when I bulk up with body exercises, weightlifting? Hypertrophy. In general, we think that there's very little, if any, increase in the number of skeletal muscle cells once you're an adult. Okay, you don't increase the number of cells. You do increase the size of the cells you have, or what was the opposite of hypertrophy? Atrophy. And in the case of atrophy, you can actually have such a diminishment in the number of cells that the muscles may actually completely disappear, as happened in my friend who had the brain tumor. She's still alive. She retired from TJC and lived happily ever after. Okay? Still going strong. We see atrophy when people wear casts. Why? If you broke your arm, it's the bone that's affected, right? So if you broke a bone in your forearm and you had a cast on your forearm, why would your muscles atrophy? You're not using them, and if you don't use them, you do lose them. That's true. So I was watching a special on the news the other night about 3D printed casts. Have you seen that? They can print them to order. They can just take one of those 3D scanners and scan the part that needs a cast and do 3D printer, print you a cast. It's lightweight plastic. It's very strong. It has lots of openings in it, holes in it, so that the skin doesn't get all messed up from not being exposed to air. and you can scratch it when it itches. That's very important. And lighter weight, and they fit them on in 2 pieces, and they just bolt them on. So I think that's the future of casts. Okay, any questions about all of that? That's too depressing to talk about what happens with age. Everything slows down when you get older. So we'll talk about the effects of anabolic steroids, not only as performance enhancers, and this is why I was looking at pictures. If you go to look at the Mr. Universe contests, oh my gosh, some of those people have just gone to such extremes. It's really great, though, when I'm looking for pictures to test you on surface anatomy. But some of them were just too far gone. Really kind of scared. So why do people use anabolic steroids? What are they after? They're after the muscle effects. Either they are bodybuilders looking for the appearance of strong muscles or hypertrophied muscles, or they're actually looking for more strength, okay, or endurance. And let's see, what's the latest scandal on that? I guess it was the Russians. The Russians in the last Olympics, what did they do? And it wasn't just the Russians. They flunked their drug tests, and they were, a lot of them, using performance-enhancing drugs like steroids. So their Olympic medals may not have been ethically acquired. So what do anabolic steroids do? Anabolic steroids are sex hormones. In males, remember that's testosterone, and females it's estrogen, mostly. But when people take anabolic steroids, they're taking drugs that are steroid chemicals that mimic the effect of testosterone, because testosterone builds muscle. Do women do that? Yes, they do. Does it help? You know, there's a fairly common therapy being applied to women now. And you've probably seen, if you watch enough cable TV, you've seen the low T ads. Y'all seen those ads? Have you? Seriously? Low T? Heard of it? Not heard of it? You haven't heard of low T? This is one of those cultural moments that I get to share with you. Low T is a marketing adventure that is trying to get men to replace testosterone by telling them that their testosterone levels are low. Well, that's, of course, a natural effect of aging, right? Everything slows down when you get older. Testosterone levels in males will drop. When do they drop? How low is normal? And how much is a safe supplement? Those are all open questions to me. But they're marketing testosterone treatments to males whose blood levels of testosterone probably are within the normal range. But the effects of them are not only on sexual interest and performance, but also on stamina, exercise potential, strength, and all of those other things. So do those effects apply to women as well? And the answer is yes. Testosterone supplementation is being used in women as well as in men, probably at lower levels. What are the side effects? Acne is one. In women, facial hair, definitely. So masculinization of women does occur in some cases. And, So behavioral effects are kind of scary. So there's what we call roid rage. So if you take anabolic steroids and you overdo it, then men have been known to think they were invincible. They jump off of buildings. They stand in front of speeding cars. They start fights with people who are armed. I mean, like crazy risk-taking behavior, enraged behavior. And there is some evidence of an association with brain tumors after long-term steroid use. So some famous known users of anabolic steroids. Lou Ferrigno was an actor and a football player who played the Incredible Hulk in the original TV series way back, and he had a brain tumor. So we think he's not the only one. We think there's a correlation there. So to enhance above the normal values just so you have prettier muscles for your Mr. Universe contest, that's one thing. But to supplement low levels due to aging, which even though aging is normal, You know, if you can supplement it and reverse or prevent some of the effects of aging, that's certainly within medically accepted practice. Yes.
Would, I know like birth controls are saying with levels of estrogen, so would that be considered an anabolic steroid?
Estrogen is an anabolic
For
steroid.
like birth controls?
For birth control, the levels there are so low that they're not going to have that anabolic effect.
I'm just trying to give a positive example.
Oh, good. Thank you so much.
It's just like weight range and artificial.
Yeah, so when women go through menopause, it's not uncommon to go on estrogen replacement or hormone replacement therapy, and you'll see it abbreviated HRT, hormone replacement therapy. So that's pretty common. And I'd already warned you ladies about losing bone density starting when you're about 30, and that was one of the things that can help prevent it is estrogen. So yeah, it is one of the steroids. All right, we have time to get through smooth muscle, and then I think we're going to call it a day. So when we talk about smooth muscle, you really have to kind of stop and shift gears completely. And the first thing I want you to do in this gear shifting is, I haven't asked you to draw anything today, so let's draw a picture. I want you to draw a muscle fiber of skeletal muscle and an individual smooth muscle cell to scale. Draw them to scale. I'm going to give you the dimensions. Okay? A skeletal muscle fiber can be 100 micrometers across. And a smooth muscle fiber is typically 10 micrometers across. So if you draw them to scale, however big your skeletal muscle drawing is, how big is your smooth muscle drawing going to be? A tenth the diameter. Let's see if you can do that. Muscle fibers, skeletal muscle. Smooth muscle, they are called fibers, but they are. Skeletal muscle fiber and a smooth muscle cell. So try to give me like a 3D cutaway view showing the diameter and something of the length of it. You have to fit it onto the paper. One step. You do not need to fill in the details. We're just trying to get the relative scale of the two cells. So technically, you're not drawing a whole cell because I want a cross-sectional view of it, so I can see what the diameter is. So here is a cutaway view of a cell, okay? Either cell. just have to draw them to scale. You should be done by now. I gave you all the information you needed. Don't label your pictures, please. Nobody else labels. All right, size-wise, what were our sizes? I gave you some specific numbers. What did I give you? Okay, so if this is 10, how big is 100? That big. So how big is the difference between a little smooth muscle cell and a humongous skeletal muscle cell? It's a huge difference. Now, the next part of this is to figure out which one's more normal in size. Which one's normal, which one's weird? Big is normal? Big is weird. Big is weird. How big is a typical cell? Cuboidal epithelial cell is about that big. Okay? Cardiac muscle cell, maybe that big. All right? Red blood cell, that big. So how weird are skeletal muscle fibers? They're really weird. They're humongous, gigantic monstrosities. They are. And what we've learned about them, because the way I introduced it so matter-of-factly, made it seem normal to you. But you remember we said they have lots of T-tubules to the interior? Why do they need them? Because they're so huge, the diffusion from the outside alone would not supply what they need. So a lot of the elaborate membranes that we've learned in our skeletal muscle cells are only there because these are abnormally large cells. And smooth muscle cells are normal. So we don't need a lot of those elaborate mechanisms. And so as we study smooth muscle anatomy, microscopic anatomy, it helps you to keep that in mind, that smooth muscle fibers are more typical of a typical body cell. All right, where do we find smooth muscle? Where do we find it? You have it in the intrinsic eye muscles. Those are the muscles that dilate and constrict your pupil and change the lens for focusing. You have it in your skin, right? We already mentioned that. The erector pili muscles of the skin make your hair stand up. You have it in a lot of your internal organs that move things, okay? In fact, if it's internal organ and it's got muscle, then it's smooth muscle with one exception. What's the one exception? The heart, okay? Skeletal muscle, skin and bones, okay? Smooth muscle, internal organs, with the glaring exception of the heart, all right? So when we look at these, what we find is that, in fact, not all smooth muscle is exactly alike. And so we divide the smooth muscle into a couple of categories, and our categories are based on how they contract. So I'm going to flip to that as soon as I can get it to go there. There we go. Let's go one more. There's a lot of too much information in this. So again, how do you know what you have to know for the test? I don't know why it's not. It should be. There we go, finally. So the definitive answer to that is to look in the practice quiz. There is not a chapter summary for this. And the main reason there isn't is I've never had the continuous period of time I need to write one. Honestly, that's the answer. But the rest of the answer is this thing does such a good job that I never needed to. Why can I not rely on this anymore? Not everybody's computer will play that anymore. But if you want to know how skeletal muscle works, look at this. For smooth muscle, I think, if I don't have it online, I'm going to post it. I have a guide to smooth muscle that I'll post for you if I don't already have it posted. All right, so when we get to smooth muscle, we find that there are these two functional categories, and I like to talk about them first because to me that's more important than getting bogged down in all the details that I just rather rapidly flipped through. So what are they? Here's one single unit. What's the other one called? Multi-unit. Okay, so the idea of single unit versus multi-unit. In multi-unit, every cell is independent of every other cell. Every smooth muscle cell is independent of every other smooth muscle cell. And because they're independent of each other, they all get stimulated by nerves. And because they all get stimulated by nerves, they all get the signal to contract at the same time. Okay? That's multi-unit. This is going to make more sense once I've explained single unit by contrast. Single unit, the cells are actually interconnected to each other. And they're connected by gap junctions. What do you remember about gap junctions? They make pipelines in between adjacent cells. What flows through these pipelines is calcium ions. What does calcium do to muscle cells? Makes them contract. Okay? But it's slower than the other kind. So if you look at single unit, the kind where the cells are interconnected by gap junctions, I'm going to exaggerate the gap junctions. They're not really this big. But imagine all these cells interconnected by gap junctions. Then if I stimulated this first one to contract, then at the same time that it's contracting and shortening, then calcium ions are flowing through to the next cell. But by the time this cell starts to contract and shorten, this one's already relaxing again. And as this one's contracting, then it's also sending calcium through to the next one. So they contract in a wave. So single unit gives you a wave of contraction. And when that term is applied to tube-like structures in the body, it's called peristalsis. So you get peristaltic waves. Can you picture it? So, for example, in your esophagus, you may have felt this before. If you ever swallowed something that was too hot or too cold and you could feel it kind of moving down, there is a wave of contraction going down your esophagus. Okay? That peristalsis is propulsive. That is, it propels whatever's in that duct and squeezes it through. So where do we squeeze stuff through muscular tubes in the body? Your entire gut. From esophagus, through stomach, through small intestine, through large intestine. Peristalsis all the way. Okay, where else? How do you get urine from the kidneys to the bladder? Peristaltic waves. Okay? How do you expel a baby from the uterus? Peristaltic waves, folks. Okay? Now, do you have peristaltic waves that make the hair stand up on your arms? It's not peristalsis. Peristalsis is propulsive. It's squeezing a tube to move stuff through it. Okay? Does the iris of your eye constrict in a wave as it goes around, or does it all go at the same time? All at the same time. Okay? Same with the lens of the eye. How about your respiratory system? Those are muscular tubes, but are you propelling air through them? So, do you use peristalsis in your bronchial tree? No, you don't. You just constrict them and dilate them. Okay? Now, how about your blood vessels? Do you squeeze blood to propel it in a wave of contraction through your arteries? Who is causing blood to circulate in your body? Your heart is doing all that work, all of it, all of it, all of it. So do you have muscles in your artery and vein walls? Yes. Is it smooth muscle? Yes. Is it single unit or multi-unit? It's multi-unit. You contract them, you dilate them. You don't peristaltic. No peristalsis in blood vessels. So always associate these single unit things with peristalsis. Now I know that screen right there says most blood vessels. I'm telling you it's not peristaltic. Okay? So I'll email Valerie and ask her if she's right on that or not. Or I'll look it up in the book because I've just now noticed it. See right there? Big question mark. Because I've always thought it was multi-unit, and this is the first time I've noticed it's there. Okay, same with respiratory. Let me check on that. Okay, so look what you see here. Arteries, air passageways. So the larger ones definitely multi-unit, and that may be where I was focused. Okay, so what does single unit have that multi-unit doesn't have? Gap junctions. What does multi-unit require that single unit does not require? It needs its own nerve stimulation. Every muscle fiber has to have receptors for the neurotransmitters. Okay, there are a lot of differences between skeletal muscle and smooth muscle. One of the main ones is that it's not striated. So rather than flipping back to that picture, let me just draw you a quick sketch that's going to show you what we need to know. So if that's a smooth muscle cell, we say it's spindle-shaped. then what you find is that there are structures on the surface, and this is just a superficial view, and these are called dense bodies. And the dense body is to smooth muscle what the Z discs are to skeletal muscle. That is, they're the points of attachment of the thin filaments. So now we're looking at the inside and we're seeing thin filaments scattered, but all of them attached to dense bodies. When I get ready to look at the thick filaments, what I find is they're just kind of randomly scattered end to end, and there aren't as many of them as there are thins. So do you remember we just said that when you stretch skeletal muscle too far, it can't contract because the myosin heads can't reach the actin? That doesn't happen here because the individual thin filaments are not dedicated to a specific thick filament. It can stretch out and just find a different thick filament to contract. Okay? So the fact that it's not striated makes it able to stretch more. The membranes are a lot more flexible, and if you look at the membranes in extreme close-up, what you see is folds. So that when you stretch it, there's some room for expansion. Think about that the next time you decide to eat more than you probably should. So what's happening to the smooth muscle cells in the lining of your stomach or in your urinary bladder when you have to hold it longer than you should have to? Those smooth muscle cells can really stretch and still contract, much more so than skeletal muscle can. Okay? But stretching them doesn't mean they don't do anything. When you stretch a smooth muscle cell, you actually stimulate it to contract. So this is called the stress relaxation response. And yes, I'm going to expect you to remember that next semester. Smooth muscle, when it's stretched, will respond by contracting. But then it will relax. Now, it's basically a muscle twitch that's triggered by stretching. But whereas a skeletal muscle twitch, if this is a graph over time, in a skeletal muscle twitch, the stimulus is here. Go back to a skinnier mark. This is a skeletal muscle twitch. Up, down, relaxed. 30 milliseconds, 10 to 100 milliseconds. This is a smooth muscle. That's one twitch. And it can last hundreds of milliseconds. And how much tension does it generate? Very low, right? Because it's just a little teeny tiny wimpy cell. Unlike those giant, abnormally large monstrosities of skeletal muscle cells. Okay? So why does this matter? Well, a couple of things that you may or may not have noticed. Sometimes when you've eaten too much, your stomach feels tight and then it kind of relaxes. Your urinary bladder will definitely do that. So your urinary bladder has reflex reactions to, it stretches a certain amount, that triggers it to contract. However, if you have good sphincter control, then you prevent the bladder from emptying. And then it relaxes. So the urge to go disappears until it stretches a little more, and then you get another urge. And you have to really fill it pretty full before you've kind of gone too far. Okay, so that's the stress relaxation response. It's very important in regulating blood pressure. What happens to an artery when you stretch it? If you get a boost of blood pressure to a little arteriole, what's it going to do? It's going to contract reflexively. That's going to prevent that burst of blood to go through to a capillary and break the capillary. But then it's going to relax, and as it relaxes, that lowers the pressure. Okay? So please remember the stress relaxation response. It's a natural reaction of smooth muscle. So smooth muscle can be triggered to contract by more than just a nerve stimulus. Skeletal muscle, that's it. You cut the nerve to it, it's paralyzed. Smooth muscle, depending on where you are, stretch will make it contract. So as you swallow, what are you doing to the muscle in your esophagus? You're stretching it out.
and that triggers that peristaltic wave. As food moves through your gut, same thing. You know, yes, it's augmented by nerve impulses, but it just the stretch alone can make it contract. And that's true in the uterus as well. Anybody that's given birth knows. Stretching the uterus wall will cause contractions. Anybody that's carried a baby to term knows when they kick late in pregnancy, you get a contraction because they're stretching the uterine wall. Okay, so what else do you need to know? The nerve control of the smooth muscle is autonomic. That's the term we use for involuntary. And the thing about involuntary or autonomic contraction is that unlike skeletal muscle, you can inhibit it or you can stimulate it. So you can tell it specifically not to contract. Can I do that with skeletal muscle? Skeletal muscle has an on-off switch. It's either contracting because you turned it on or it's not because you turned it off. You should think of smooth muscles having like a dimmer switch. So I can turn it down and turn it up by secreting inhibitory or stimulatory neurotransmitter or hormones. That's the other thing. Hormones can stimulate or inhibit smooth muscle. So during pregnancy, some of the hormones from the placenta actually inhibit uterine contractions. And it's only late in pregnancy that that hormone level drops off and you start having contraction. Okay? And the stimulus is not always acetylcholine, although it often is. It doesn't have to be. So you see acetylcholine on this slide, right? ACH is acetylcholine. But there's another neurotransmitter, norepinephrine. And we'll abbreviate that NE. And we'll study it more next week. Okay so far? Questions at this point? All right, I'm going to leave for you to study online the attributes of smooth muscle. And I'm going to post for you my guide. When you see this diagram that shows you all these steps for contraction, I have a very important clinical term for you. What is that? Too much information. Okay? You know, the more we learn about these cellular signaling pathways, the more enamored we get of them. I dig this stuff. But it's impossible for us to expect you to learn all that. It's just crazy. So you probably should remember calmodulin. I know it's tiny up there. And we already knew that ATP stimulates the myosin heads. But I'm not going to ask you those signaling pathways. That's just way too much. It's a very pretty picture, though. Okay, so the way that smooth muscle works and the way that skeletal muscle works are entirely different. Remember, calcium was regulated by troponin and tropomyosin in skeletal muscle? You don't even have that in smooth muscle. We have calmodulin instead. But like I said, that's just really way too much information. Okay, so learn the basic differences between skeletal and smooth. Learn the locations of smooth specifically for single unit versus multi-unit, and understand the different ways that you can stimulate contraction of smooth muscle. And I think that's probably going to be enough. Make sure you study the practice quiz on that, since there's not a chapter summary on that. Any Learn Smarts on smooth muscle, be sure you focus on those. And before I leave today, I'll make sure I have my guide to smooth muscle posted. I don't think I do right now. I just flat don't remember, so I'll make sure it's up there. All right, does anybody have any lingering questions? What are you going to do Monday? You're going to take my test and you're going to go to CAP. Don't forget to go to CAP. And then Tuesday, you have a quiz in lab, right? So it's business as usual next week. I will be around this weekend. If you have questions, you can send me an email. And other than that, I'll see you on Monday. We'll start the nervous system.